I would like to pass on to Fernando. Fernando represents VirustTotal. I met him in Japan, so for two Europeans to meet in Europe is highly unlikely, but apparently we met there, and I'm glad for you to be here. Fernando, please.
Thank you. Well, hello everyone. I'm Fernando, and I'm glad to be here. I want to thank the organizers for this event and also for the invitation to be here. And the talk of the name today is Practical Frida. So I'm going to do some warnings first. There's reverse engineering, so there's also live coding, so something could go wrong. And for those who don't know Frida, I'm also going to be doing a very brief introduction of what Frida is and binary instrumentation. So I hope you enjoy it. And also, I won't be here for long. This afternoon, I fly back to London. So if you have any questions, please let me know or just take a screenshot. So I'm Fernando, and I work as a software engineer at VirustTotal. And my main focus is the development of sandboxes, so dynamic analysis environments. And I also enjoy reverse engineering banking Trojans. So you will see that what we are working today with is also banking malware. And regarding the Frida topic, well, I authored a website which is completely free. You can visit it anytime, where you can learn how to use Frida and how to instrument applications with examples. It is not a heavily theory-based website, but just with practical examples you can copy-paste. And well, these are my contact details in case you're interested. So let's start with the talk. And the actual talk is what is binary instrumentation. So binary instrumentation consists on injecting instrumentation code, which we will see later how that works, that is actually transparent to the target application. And that way we can obtain behavioral information on what's happening in the process. So it's not only that we're able to monitor what's happening at the instruction level and also at the code level, but we can also manipulate the workflow of the application. So we are able to alter what paths it's being followed, and we are also able to extract information and alter it to our necessities. So as I mentioned in here, you have access to pointer data, memory data. You can modify memory pages. You can monitor return values. You can monitor arguments, anything you want. So what's Frida? Frida is one instrumentation toolkit, and it is some sort of grease monkey. I don't know if you know the extension for native applications. So the idea is that you're able to perform binary instrumentation using this toolkit. And the advantages over other toolkits is that it provides this high portability, and also that we can use JavaScript to write our instrumentation code. So the idea is that you write code in a high-level language, you abstract of the most difficult parts of writing that code, and Frida gives us that interface to us. And also, it's highly portable. You can install it on Mac OS, you can use Linux, you can use Windows, and the target OSs are also widely supported. You can instrument a Mac application, you can instrument an iOS application, you can instrument an Android application, etc. So there's other instrumentation frameworks, of course. We have Intel Pin, we have Dynamo Rio, we have IDAS APP call, which is not exactly the same, but somewhat it provides us with similar capabilities, but they all have some problems, right? So Intel Pin, you have to pay for the license, so that's one thing there. Dynamo Rio, you can use it, but again, you will have to deal with C, C++, so you will have that complexity. It will make the development slower. And then you have IDAS APP call, but you have to pay for the license. So with Frida, it's free. The license is very permissive, and you have access to the code. So anything that doesn't work, you can actually push a fix, and it's actively developed. So essentially, what advantage do we have over the other frameworks? Well, as I mentioned before, you can use JavaScript and you can use TypeScript. But we are not limited to these two programming languages. We can use C directly, but it kind of defeats the purpose of using frida, because what we want to do is write instrumentation code very quickly. And of course, there's huge cross-platform support, cross-architecture support. It's not only x86, we have also ARM, you can MIPS, there's several architectures that we have access to. We also have the toolkit, which is a series of command line tools that we can use to list processes, to get a command line with frida. We can also automatically trace without writing any tracing code. And there's lots of examples. There's community examples. There are GitHub repositories with code examples. So probably any problem that you might find when using frida, it's already solved by someone in the community. So how do we set up our environment? As I said, it's highly portable. So this is the only thing that you have to do. If you have Python, in the pip package manager, you just write pip install frida and frida tools, and then you will actually get the whole thing installed in your computer. Then from here, you can start working without anything else. Well, of course, today we are going to be working with an Android application, so we need some auxiliary tools to actually instrument, because we need to know what we are going to work with. So we need a decompiler. You can have JetX, which is free, or you can use GEB. This is a commercial one. And then you need a disassembler, because there's sometimes where libraries are needed to be reverse engineered. And of course, you need a target application. You see that I have highlighted here Radar2, and the reason is that there's a plugin for Radar2 called R2Frida, which is very useful for using a disassembler at the same time that you are using Frida. But I mean, you can use anything, and unless you need that feature, you can go with any other. You can have IDA free, you can use Ghidra or any other disassembler. And this is probably the last one. So the Frida's core API is mostly, the API is very extensive, but I'm going to only mention these 4 ones. You have the interceptor API, which is used to hook functions. It's not only hooking functions, you can replace functions, and you can also create native functions, which is a way to invoke these functions on your own. You have the Stalker API, which is to trace the execution at the instruction level. And then you have 2 special APIs, which are limited to mobile systems, which are Java API for the Android runtime, and Objective-C for iOS and macOS applications. So essentially, you gain access to Java classes, Java methods, etc. Here's the documentation, but this is called Practical Frida, so we are going to get our hands in actually using Frida. And I will explain what's happening in real time. So the initial idea was to show a crack me, but during the flight I said, well, let's go with the real thing, and we're going to play with real malware. So I promise this is the last slide. There's more slides if you want to check more details later, but from here on, it's going to be hands-on thing. So this sample that we are going to work with is Copper. It is an Android banking malware evolved from Exobot, and it is a multi-stage setup. So I chose this malware because we are going to have to instrument native code and also Android code. So essentially, I'm of course not going to reverse engineer the whole thing. We are going to deploy. And what it does is that once you execute this application file, it loads a hidden index file, which is hidden in the resources section, which then loads another library. And that library is the one in charge of decrypting the real payload. And then another payload is stored in the cache. This sample does not actually delete the cache, so we have that advantage to us, but we could solve it. And some more interesting things is that, well, the data to the command and control is sent as a JSON object, and it uses a repeated list, rotated list of domains. So if one of the domains doesn't work, it's going to try to use the next one. So our first objective is to manage to get the rotating list of domains and the information that it's sending automatically. Right, so I have here an Android emulator. I hope you do, yeah, it's starting up. What I'm going to do first is I'm going to access the emulator. And I'm going to run the frida server. Sorry, we need to. So we need to run the frida server first so we can connect to the device. Otherwise, we will have to repack the application and bundle frida inside. So we are going to go with the simpler path, which is just running the frida server. From here, we can connect to our Android device to the frida server. But first, let's try to figure out something. And if we go to, well, this is a behavioral report. And the only thing I want you to check is that if we go to here, there's a file written to disk called cache. SVC PMG. So we already have the cache here, and it's probably calling the fopen API. Another thing I want you to check before that, I'm going to open the copper file. Yeah, it's here. So if you see the decompiled code, this is the package name. There's no code here, so this is already suspicious. There's a mention of that drop file as a raw resource, and it is in this address. And then if we check the resources, we check the manifest, we see that there are mentioned two classes that are not in the code. So this pretty much tells us that something is going off. We have here a library, which is a library I have never heard of, so probably suspicious too. And then if we go to assets, well, there's PNGs, there's WebPs, there's JSON files, but one of them has a weird name, and well, it is most likely not a JSON file. So one of these is the actual real payload, or it is embedded in this one. And let's try to get a handle of where this is being extracted first. OK, so this is skeleton we're pushing in here. And the first thing I'm going to do, I'm going to get a function pointer to fopen by calling the getExportByName function from frida. So this, what it does, it is returning a memory address to this fopen function, which we will need. I'm going to demonstrate that by logging it to console. And now we can call the interceptor API. So on the interceptor API, we have access to two callbacks, the onEnter callback and the onLeave callback. So each callback, this callback onEnter gives us access to the pre-execution state of the function. So it means that we can monitor the values and anything that happens before the actual code works. And the onLeave callback, we have access to the return values and whatever was modified during the function execution. Since we only want the file name, the first thing we're going to do is we are going to remove the onLeave callback. And I'm also going to read the first argument of fopen as a UTF-8 string. So frida doesn't know what this argument is. It doesn't know how many arguments they are. So we need to tell it to read this memory address. We can log it here, for example. We can just tell it to read this memory address as an UTF-8 string. And then we can use frida to get a backtrace of what's happening, so we can find out where this is actually coming from. So we can use the thread API. There's the thread backtrace, which returns a backtrace again. And it receives the context of the current execution. And we can tell it to use a backtracer. So there's two. There's the fuzzy tracer and an accurate tracer. So in this case, I'm going to be using the fuzzy tracer. And since what it does is to return a list of callbacks, what I'm going to do is to map each one using the debug symbol from address API, and then join it in new lines. So essentially what this is doing is we get a list of the whole backtrace. When this function is called, we are restricting it to this context execution only. And then when what this does is that it tries to resolve the function name from the address of the trace, the backtrace. So let's try to test this one out. With the command line tool, we send a JavaScript instrumentation script here, which is called CyberChess.js. And we attach to the com is called 0 package. And the -u parameter is just telling us to attach to an Android device. You can see here the package name is actually that one. So if everything went well, there should be no red here. OK. Everything went well. And let's do it better. And let's change it for console warn, and this one for error, so we can see it better. OK. So we have here the backtraces. This file is not really interesting to us. This file is not interesting to us. But this one, you have seen it before, right? It's actually interesting. So we get here that this file was last called from this offset. So this library that we have seen here before in the asset, sorry, in the lib section, was the one responsible for opening this file in the directory. So we are going to copy this in a notepad, for example. Sorry. And I'm going to get the base address of this module. So frida returns us the this frida resolves for us which is the current memory address of this module. And what we are going to do is that we are going to open it in a disassembler, for example, IDA. And I'm going to push the library here. Of course, I'm skipping getting the library. It is not important. So I'm going to rebase it. And let's see where it is. Segments, rebase. We have now rebased it to the current execution. And we see here this is the memory address from where it was called from. So if we jump to this address, we are now in the function responsible for calling fopen. So you see this weird name. Here it is a Java native interface function. It's first calling fopen, then it's calling fwrite and fclose. So this is already suspicious. It is most likely receiving the decrypted dex file already here, and it is just writing it to disk. So why is it important to reach this point? OK, so with Frida, once we start instrumenting from scratch, when the application starts, it doesn't have access to the Java classes at first. So for example, these ones that we have seen here that are still not loaded, we could not instrument them because they are not loaded. So we need to find a starting point to begin with. So for that, we found this function which we should monitor and start instrumenting the Java code. So I have an skeleton here just to save time because we don't have much. And I'm going to go through it very, very quickly. So what do we have here? What I'm doing is that I'm getting a function pointer to the Android version of DLOpen. So when a dynamic library is being loaded, we know it. And then we are using the interceptor API to actually intercept every function called to DLOpen. And I'm reading the argument as a string. And I'm appending it to this here, so we can share the context with these two callbacks. So every time DLOpen is called, we are getting the first argument, which library is being loaded. But we don't want to monitor we don't want to react on every library because only one of them is interesting. So what we do is that once the function has finished, the library should already be loaded. We check that the library is the one that is interesting to us, and then we instrument the function that we have seen before. So once that function is then called, this one here is called, then we can start instrumenting the index file. And then up here is the actual code for the Java side of things, but it is empty. So if everything goes well, this console log should pop up, instrument init, and then this one should not crash. So how do we get the function pointer for this one? What we can do is that we can get the base address of this module. And then we need to calculate the address of the function that we want to instrument, which is this one. So in our notepad, we have the offset here. I'm going to copy the whole thing. So we have here our offset. And then we can get the decrypt function, which is the base address plus the offset. And we are casting it as a pointer because what we get here is the addition of this memory address plus this offset. So we need to cast it to a pointer. So if everything goes well, let's see. Let's instrument. OK, we get the memory address, and we also get the instrument init. So it means that we have reached the point when we are able to instrument the Android code, the Java code. So we have already hooked the decryption function, and we are at a very good point. So the next step is I'm going to skip through the whole decryption part, and we are going straight to the final payload. And I'm going to open a second one here. This is the final DEX file responsible, well, that appears after the whole decryption thing. So if we go here into this package, you start seeing some familiar names, right? So if you check here, we see P015W. It is most likely to be here. P015W, yeah. So we have it here. So this is most likely what the actually code is in. And then there's another auxiliary class which has access to, well, which is the code for the malware itself. So the idea is to automate the things that are interesting to us. And for example, one of the things I mentioned before is that it rotates a list of domains, and then it sends information using a JSON object. We are not going to statically and reverse engineer the whole thing, etc. We are just trying to do it as automatically as possible. So one of the functions here, JSON object, JSON object. Let me see if I find the interesting one. Okay, no, not this one. This is live, so if anything, okay, I got it. So this function is receiving a string and a JSON object. And then if we check the code, it is performing or trying to perform an HTTPS request. So anything that is going to be sent to the command and control is most likely here. And this string, str, is the URI. So we will most likely get the URL here. So how do we instrument this thing? So the first thing is getting the reference to this class using frida. And the real class name is this one. So the compiler just renames it. And let's get to the code. In this Java perform block, the Java API is active. So only in this code block we can instrument Java code. So the first thing is we're going to get a reference to this class by calling the java.use API. And I'm going to log what this is actually. And now we need to choose which function, which method to instrument. So if we go to our code and we go to the previous function, where is it? This one. The function name is goto. So, well, it says this one here again, but it's been renamed. So the real function in memory is going to be this one. What we do is that we access this class and we choose the goto method. And then we overload it. We choose the one that is receiving a Java string as first argument and a JSON object as a second argument. And then we access the implementation. We are going to replace the function itself. And we are going to write a function here with C2 as first argument and payload as second argument. Right, so since we are modifying the function, the first thing that we need to do is to allow it to run as usual so the application doesn't crash. So we do that by calling the original function with the original arguments, and we return the expected return value, if there's a return value. So now we have the command and control and the payload here. If everything is correct, we can now log the command and control. And we can also log the payload. Let's see if this is actually working. And well, I'm instrumenting DL open, so this causes some unexpected behavior. So we are this, as you see here, we have this class, which is the class reference, which we have gotten here. And there's still no messages being printed, but if we start interacting with the application, okay, we are getting the command and control. You see that the next one is a completely different URL. The endpoint is the same, but the URL is different. And well, it's also trying to send the IP address and information of our device to the command and controls. Don't worry, the command and controls are offline, so nothing is being actually sent. And if we continue executing the application, okay, it's trying to even send more details of my machine, my ID, my system properties, my operator, my applications, etc. So now we are able to instrument and get all the information from the execution just by monitoring this. So this is only one sample, but you can grab a different copper sample. You throw the same instrumentation code. You start extracting IOCs. You start instrumenting any payload. And also, you get access to these keys. So you can find references to these keys in the code. And you will see where this is actually coming from. So probably if I type TF, we are going to see that it is coming from this function, and this function is the one responsible for getting the content here, right? So what else could we do? So one of the first things that I noticed when I opened this sample is that, let me try to find, okay. There's some calls to a function called FDDO with an obfuscated string. So what we will usually do is find the decryption routine and extract it, well, isolate it and run it through all the strings. But we could just monitor every call to this function and keep a list of what each of these encrypted strings actually stand for. So if we go to the definition of this method, it receives a single string and it returns a string. essentially what we get is the obfuscated string, and here the returning string will be the decrypted string, the deobfuscated string. So we could instrument it. Let's see, the class name is called FDDO break. And what I'm going to do is I'm going to comment this one out because it's going to be very noisy if we have the monitoring here in the console. So we are going to replicate what I did before. So this time I'm going to get the reference to this class, and then I'm going to get the interesting method, which is FDDO. If it's here, FDDO, and it receives a Java string as first argument. Right? So another important thing here is this overload parameter. It is possible to define several methods with the same name, but with different arguments. So what we do with this overload is that we choose the method FDDO that receives a single string as a parameter. If we don't specify this one and there's more than one method with the same name, Frida doesn't know which one to instrument. So for that one, I will always call this overload function to choose the one that is interesting to us. The same way, if we don't specify the correct types, it will also tell us that it can't find the function. So we are replicating what we did here. We capture the return value of the original function. And in this case, it is the encrypted string. And we return the original one, so the application doesn't crash. And in reality here, the return value is the decrypted string. So we can rename it. And I'm going to be logging to console. Again, the encrypted string. And sorry, let's do it this way first. We're going to write that this encrypted string is equal to the decrypted string. And the thing is that this function might be called many times, and we only want to see the same string only once. So what I'm going to do is I'm going to define a list, cache, crypt cache, for example. And I'm going to check if if this crypt cache includes the encrypted string. And if it doesn't include it, then we are going to log it. And we are also going to push it to the list. Right? So essentially what we are doing is we are calling the original function. We get the decrypted string. We check against our cache that this string that we didn't see before. And then we log to console what the encrypted string equals to. And then we push it to the list so that we don't see it again. Let's see if everything goes well. I'm going to again close my Frida instance. Right? So we get the instrument in it, and we get this string equals main, this string equals last request, this string equals this one, this string is HTTP, this one is register. We don't need to do anything. Every time this function is being called, we get the actual output of the decrypted string. So, well, we can also push it more. I mean, we can do something more, and we will continue printing. But essentially, this makes our work way easier. So another thing we could do, for example, is monitoring the shared preferences. So let me, okay, yeah, it goes on. It will continue the whole execution. And let me showcase one last example. I'm going to go to the application folder and the shared preferences. And in the shared preferences, there's lots of information being stored either for backup purposes or temporarily. So we want to see that every time that this shared preferences file is being consulted, is being queried, that we get what is querying. So this one, we need to get a reference to the shared preferences. And we use the java.use API. And we access the implementation. Sorry, I always forget it. So we access the implementation of shared preferences. And then the method that we want to instrument is the getString method. And we choose the one that receives a Java string, again, always with the strings. It's two strings, so you get the Java lang string. Sorry, there's two. So this one is the value and the default value, I think. So this one, you don't need to reverse engineer it. You can find that the android.app.sharedpreferences implementation has this getString. It's in the official documentation, and that it receives these two parameters, right? So again, we get the return value by calling the original one with the value and the default value. We return the value, but actually the return value is the contents. So we are going to change the variable name, and we are going to log this one out. So we are going to do that the key is equal to the value, the original value received, so we can check which key is being consulted. And then the next thing is getting the actual content. So we are going to, value is going to be contents. Let's see if everything went well. I hope so. So we're going to instrument it. Okay, no crashes. No, okay. We get that it is consulted the VNC key, but it has no value. The block push apps is not set because the command and control is not responding. And if we continue with the execution, let's see if something pops up. Okay. This inject ACCB key is storing a JSON file or JSON object, and it is the HTML responsible for trying to trick the user, which is not loading at the moment, into giving it the necessary permissions. You see here, install services, bot name. It has checks for these three languages, Spanish, German, and English. And well, this bunch of code of HTML code, which is used to overlay a trick over the user. There's more here. The key, they are trying to store my real IP address. Then, let me see if there's something here. The list of domains. So you could just monitor this key, the domains key, and get the complete list of rotating domains. Or you could monitor the first thing here that we did to get the command and control and the payload for research. And well, this is with this way we have pretty much defeated this sample. We can it is already generalized. So the only changes that we will have to make here is that when we are instrumenting, we need to change the package name, but that one is trivial. And the code is going to be pretty much the same for this malware version. So this is it. I know it's very technical, but I hope that you have enjoyed it. In the slides, there's more. It goes a little bit more in detail of what's actually been happening. And that's it. If you have any questions, please let me know.
Thank you. Just to carry on with what you said, if it was too technical, I mean, the idea was that it is indeed technical, and if you understood everything, well, maybe you didn't learn much after this. If you have something that you don't understand, then you can expand your knowledge further. However, my next question is to you, because we talked with you about that this frida was picked up by you because you wanted to automate the malware reverse engineering analysis in the VirustTotal. How much automation can be done on this sample in the VirustTotal as of moment? Because you did a lot of manual tasks in which you said, oh, this is an interesting function. Let's look for interesting function. How much can be automated?
Okay, well, that's a nice question. Well, in the case of if you want to get some specific information from a sample, from a binary, you need to reverse engineer it and figure out which function, which offset is the one interesting, so you can generalize it. But usually the most interesting things are done by using system APIs. So we have here the example. In what we have now, we have instrumented this very specific function to get the payload. Sorry. So in this function, we have gotten the very specific function that it is not generic, of course. But the shared preferences one is generic. So any call to share preferences from any legit or malware application is going to use this one. So what we do is that we instrument the ones that are system APIs that are going to be called for sure.
Right, but finding interesting functions, can that be currently done already in the VirustTotal automatic sandboxing, or this is still where reverse engineering has to be done by the human and then carrying on with this?
For specific functions, yeah, it requires a human, and yeah.
Yeah, so that's what I understood as well. Yeah, human is still in the loop. We can't eliminate the human out. So the question's also about the current malware, especially for the Android malware. Have you seen that the malware has been trying to counter the instrumentation and reverse engineering? For sure, we know that malware authors try to counter this to make it harder. How prevalent that is?
Yeah, actually, the original idea was to show up a crack me with techniques used by malware, or well, not just malware, legit applications. They don't want to be reverse engineered. They don't want to be instrumented because they could bypass their SSL communications, etc. So in that case, there's techniques, of course. They try to detect the frida server that we are running here. They try to detect it with strings, with memory maps. So yeah, there's techniques, but there's also ways to go around this.
Right. Is there any question from the audience? Yes, there is one question. I mean, Carlos was the first one with the hand up, so Carlos. Oh, hold on.
Sorry.
Wait for the mic.
Sorry. Hi, I'm Carlos with CERT.LV. My question is, those decrypted strings, can you push it back to the disassembler or to the this Android environment? Because when I was doing reverse engineering, it's really helpful to have the decrypted strings as comments and then to read it in the disassembly. Can you somehow, does a frida provide way to get those some decrypted strings that you can attach as comments in disassembler or so?
With frida, you will need a memory address to attach to. You could read the memory sections to extract the strings, and you could write. There's an API called memory access. So, for example, let me find it. So this memory access monitor, what it does is that you tell it a memory address range, and then you write the bytes that it is trying to access. So if in this case it will be a string, it will react if something happens based on your conditions. But it is not. It doesn't have that exact functionality. It is very. It gives you the framework, but you have to do lots of things on your own.
Thank you. But thank you for the very entertaining presentation.
All right. Thank you. The time is up. So let's give an applause to Fernando.